This will be lesson 1 of chapter 3, and in this chapter we're talking about atoms. We'll talk about in detail about the basic unit of all matter. So we'll begin with this question and a picture here depicting what an atom is. If you take a piece of metal, in this case something like magnesium metal, and cut it in half, and then if you keep cutting it in half, eventually you'll get to a point which cannot be cut any further. And that point, or that chunk, that part, is what we call an atom. So an atom, actually by definition, means, in the Greek, in the original, indivisible. Meaning you cannot divide it further. So a little atom in this piece of matter is something that you can no longer divide. And all matter, anything you have, can be taken to this level and you can reach the atom. So here is the definition. It is the smallest unit of an element that maintains the properties of that element. And we defined an atom in the previous chapter. Here it is again. Think through this definition. And you usually are probably used to seeing atoms represented with figures like this. We'll describe in detail every portion of this figure, but we'll define it as the smallest unit of an element. We also define an element. Why not we do the same thing again from a different perspective in this chapter? So an element, by definition, is made up of only one kind of atom. So again, atom and element, the two definitions rely on each other. So here you have three different elements. This is actually chlorine, the element chlorine. It's a gas. It's a nice green colored gas. And if you were to look, you'll only see one type of atom in the midst of this gas. Here is bromine. Bromine is a red liquid, my favorite red liquid. And here is the element sulfur. In all of these cases, if you were to look deep inside, you would see only one type of atom comprising these. However, the difference between these atoms, or these elements, would be that they're made of different types of atoms, as we see. Okay, let's go ahead and go into the details of what an atom is made of. So we'll first define an electron. And an electron is the smallest part of an atom. It's a very tiny particle. It can be said to be orbiting or going around the nucleus, which we'll define as well. The electron's mass is extremely tiny, 9.11 times 10 to the negative 28. Negative 28 is very, very small. This is a very tiny number. It also has a charge, an electrical charge, and its charge is negative. So all of these, we'll call these subatomic particles, particles within the atom, like the electron, will have both a mass and a charge. Now, you can think of big objects like yourself having a mass, but you don't really think of big objects having charges. Really tiny particles do have charges. So on the atomic scale, we'll also talk about this property of matter, the charge. Okay, the nucleus then is a very dense region of the atom which houses and which exists both the proton and the neutron, which we'll define in more detail here in a minute. And the nucleus is thought of as occurring in the middle. You may be aware of this. The nucleus is the middle, the exact middle of the atom. Now it's very dense. In fact, most of the atom is made by the electron. This is the electron that's traveling around the nucleus. Most of the size of it. And the electron is, the nucleus is actually a very small point inside the atom in the middle. Let's go ahead and define in detail what we see inside the nucleus, and that is the proton, which is a nuclear particle, means it's in the nucleus. It has a mass of 1.67 times 10 to the negative 24th grams, also a tiny, very, very tiny mass, just like the electron, actually bigger than the electron, but on the same scale. And it has a positive charge. So again, its mass and its charge. The neutron is also a nuclear particle, means it exists in the nucleus. Its mass is the same, notice, as the mass of a proton, the same exact mass. But its charge is 0. It is neutral, it has no charge. So these both exist in the nucleus of the atom. We're going to talk about a few experiments that help discover these particles. The first is called the gold foil experiment. This was done by a gentleman called Earners Rutherford. And I'll show you a picture of this in the next slide, but this was used to discover the proton residing in the nucleus, very dense nucleus. What he did is he took a gold foil, thin gold foil, a piece of gold sheet, and then he bombarded it or shot it with a bunch of what are called alpha particles. Alpha particles are actually positive little particles. What he found is that through the gold foil, most of the particles went right through. Nothing happened. And only a few were actually deflected, meaning only a few shot back. So let me show you what this experiment looks like. Here it is. And this gold foil, now remember the gold foil is made of atoms. And there's a bunch of atoms in here. However, most of these particles did not hit the atoms, but went right through. Only a very few hit the atoms and shot back. And this told us that most of the atoms are actually comprised of empty space, and only very, very tiny points of it have matter in it. This is mostly just electrons, and only very tiny spot in the middle of it has a nucleus which has actual matter. And this led us to the remarkable discovery that matter is mostly empty space. Very strange statement, but very true. The other experiment that was used to discover the electron was called the cathode ray tube experiment. And what we did here, we took a tube and filled the tube, or connected the tube with electrodes. This is connected to electricity. And then we allowed electricity to go from this side to this side, and it created a strange looking ray. We call this the cathode ray. What this ray was made of were electrons. And in fact, this tube was partially evacuated, which means air was sucked out of it, and only then can we see these electrons. This was the famous discovery of the electron. By the way, the cathode ray tube, the CRT, is what our early television sets were made of. Now we have flat screens that no longer use it, but the CRT is your television. Here are the relative masses of the different subatomic particles. The proton has, now when I say relative mass, I mean mass in relation to one another. Remember, they do have absolute masses, really, really tiny masses, but if you were to compare them to one another, the proton and the neutron have about a mass of 1. In other words, they're about the same. The electron, on the other hand, has a mass of 0 relative to the proton and the neutron. What this is saying is that the electron is so tiny that in comparison to the proton to the neutron, you can ignore its mass. And it does have a mass. If you were to calculate it, it's about less than 1,000th of a proton and a neutron's electron. 6/10,000ths of one of these. So really tiny. For the most part, we can safely ignore it. Now, here we're measuring in a unit called AMU. And this unit is a special type of unit that was created to measure the masses of really tiny things like atoms. In fact, the A stands here, you'll see, for atoms. So we have to use a special unit. We can't really use grams because they're so tiny, and that's the idea. So let's actually talk a little bit more about this unit. So AMU stands for atomic mass unit. And it describes exactly what it measures. It measures the mass of atoms. Now, this is also known as a Dalton, and the reason it's known as a Dalton is because it's named after a very famous scientist who helped come up with this, Mr. Dalton. So the AMU, 1 AMU, is equal to about 10 to the negative 24 grams, an extremely, extremely tiny, very, very tiny amount. And this makes sense because atoms are so small that it's almost impractical to weigh them. So we can say, for example, that if you have an atom like lithium, the mass of one atom of lithium is 6.94 AMU, or 6.94 Daltons, dA being the symbol. So let's discover about Mr. Dalton, because he helped define a few very important concepts in chemistry. He was from the 1800s. Actually, he was born in the 1700s and then died in the 1800s. So right around 1800, he came up with these 4 statements. Let's quickly analyze each one of these. The first one says that all matter is made up of tiny units called atoms. And we discussed this. He was the one to formulate this first statement. Atoms are indestructible and indivisible. You cannot destroy them, and you can't divide them. You can't take an atom and divide it further. You cannot do it. All atoms of one element are exactly alike, but are different from one element to another. So lithium, the element lithium has one type of atom, the element oxygen has another type of atom. And then fourthly, atoms combine in specific ratios to form compounds. So for example, anytime you want to combine lithium and oxygen, it'll always combine with 2 lithiums for every 1 oxygen, always. And those are the 4 rules. Take a look at them, see if you can understand what these rules are saying. And we'll actually finish up with a few detailed discussions of these rules. Rule number 2, talking about the indestructibility of atoms, actually is a law. And this is called the famous law of mass conservation. The word conservation, remember, means it's conserved, it cannot be changed. And this law essentially says that mass is neither created nor destroyed whenever you're undergoing a reaction, whether the reaction is physical or chemical. We have a quick picture here of some reactants placed in a flask and a test tube. And the mass, notice, is 300.23 grams. We're going to shake this up, have the reaction go, and after the reaction, the mass is exactly the same. If you were to measure the mass before and after, it would be exactly the same. Even though a gas may have been created, the gas did not lose any mass. You can actually measure the mass of the gas. This is called the law of mass conservation. Very important principle. And then the 4th rule of, or the 4th statement of John Dalton was formulated into the law of definite proportions. And this referred to how atoms combine into a compound. Again, you can think of hydrogen and oxygen as the other example, making water, and water has exactly 2 atoms of hydrogen for every 1 atom of oxygen. And this is always true. Any water molecule that you grab will always have this. So every sample of a compound contains the same exact proportions by mass. So another example here is salt. If you take a look at table salt, and this is sodium chloride is table salt, which we've discussed a few times already. But if you analyze every little grain of salt, take this little grain of salt and analyze it, take this little grain of salt and analyze it, you'll always find that it's exactly the same percent by mass. Always about 40% sodium, always about 60% chlorine. Never changes. So this was Mr. Dalton's insight. Make sure you understand all 4 of these and be able to answer questions or think about answering questions. In fact, questions like this. We'll finish up with this one. Try this practice problem on your own. Tell me whether these statements are true or false. Go back over them in the notes as needed, and we will see you in class.